Hello friends, I'm very happy to come back to you again for the session 29. So welcome you all. Let us see what we will be covering today. So today's focus will be on MMU. Okay. So basically how the virtual memory is supported by ARM. So the MMU is the hardware module which can be integrated with the SoC if the designer would like to have a virtual memory support in the system. And then if we buy a MMU module from ARM and if we need to configure it based on our needs, we should have a good knowledge of how does MMU control the virtual memory support. Now how does it provide the support and how it can be configured, similar to how we learned about cache memory controller. So this discussion will be focusing on what are the support features available with MMU and how do we configure it. Okay, so there is a whole lot of program with a sample example also in the book, that one of the references that I have mentioned, that is ARM Systems Developer Guide. So what I will be doing is to make you understand what are the features supported by MMU and what are the coprocessor registers which help us in achieving the configuration of MMU. Okay, and then if given a system requirement, how do we go and change them is a good example is there in the book, and I think with the knowledge that I am going to share about the support provided by MMU, you should be able to understand that example which is shown in the book. Okay, maybe we can take it up as an assignment so that you go through that piece of software written for a better understanding. Very good. So this discussion in this class we will talk about what are the differences between MMU and MPU, okay, which I touched upon when in the last session when I explained in detail about MPU, and then page table also you are now familiar because of the session in the last session I touched upon MPU prior to that. So let us see what all is support provided by MMU in those given by ARM. Okay, what are the page tables supported and how we can configure it, what are the control registers we need to be programming, and then we will see an example system which is given in this developer's guide, and then I will just briefly talk about PCM to complete this discussion on memory. Okay, so this will be the third section. And if you consider from the memory hierarchy, this is the sixth session that we talk about memory. So this will be the last session we talk more on memory, because then we will move over to tools and then other parts of the ARM SoC. Okay. So what is memory management unit? These are all you are already familiar. That I will just summarize it here. MMU simplifies programming of application tasks because it provides the resources needed to enable virtual memory. Okay, MMU supports to use the virtual memory in building the application as well as running it in the processor with a limited physical memory. So an additional memory space that is independent of the physical memory attached to it. So we can always assume any amount of virtual memory, maybe for limited 4 GB as I mentioned, but you are free to decide or assume the existence of a huge memory in the system. You don't have to worry what is the physical memory in my system. Is it 1 MB or 10 MB or whatever it may be. Okay, as long as MMU is there, we can realize what we want. But if you have a limited memory or very less memory, then what happens is the performance will get impacted, but still the program can run in your system. Okay, maybe some minimal is there. You cannot have a very small memory and expect it to run, but it is always possible with a limited physical memory available. If MMU is there in the system and if you have configured the MMU properly, MMU when I say it includes configuring the cache, configuring the write buffer, okay, and then if you have chosen a right memory map for your application, then we will be able to run them in the system. And of course, the board that you have with along with the ARM processor and then the SoC and other memory, you should make sure that what you assume it has to be a physical memory configuration is actually there in the system. The board should also be accordingly designed, okay, or you have to modify your memory map of the physical memory based on the board design, okay, which address it is referring to, so that you know that where the physical memory is residing, so that you can configure the MMU which is coming in between, sitting in between, so that you effectively run your code on the board, okay. So let us see now. MMU acts as a translator which converts the addresses of the programs and data that are compiled to run in virtual memory. So when I say it is compiled to run, then the virtual memory what the tools assume, okay, linker and loader, they assume some location in the virtual memory. Okay, some code is residing here at some starting between some 40,000 address hexadecimal. Okay, data is maybe it is at 80,000 hex from addresses. Okay, so accordingly the code would have been generated to access these locations, because what I mean by code generated, suppose LDM instruction is there and then you have to access maybe address which is pointed to by R2, okay, and then we want to load it into R1. Now what we need to know before we use this, run this instruction, we should have made sure that R2 is loaded with proper address, right? So I could have said that move immediate maybe 80,000, okay. You can see that whether it is possible or not, because if you know, sorry, I am going writing from top to bottom, bottom to top, but I think you will be able to read it. So let me say, so move, okay, R2 80,000, okay. Is it possible to write hexadecimal? Okay, I have to make sure the 0x there and hash is there, and then the assembler will below. So if this is done, that means we are assuming that an address located at this location, we are trying to move into R1, the data which is there in this location. So this is the address which is being used by the program inside. This is the virtual memory, but actually in a system where this program is running, okay, ARM is executing this instruction, it assumes that it is accessing the address at 80,000, okay, but we know that there is an MMU, okay. We know that in the physical memory there is no address like 80,000. Maybe it varies, from 0 to maybe some 20,000 X. So this is the memory we have, and but our program is compiled and it is already there. Executable is made, and it is assuming that the data is in this location. Now, how can this program, assuming that this address is where the data is stored, will run on this system which has got a memory only up to 20,000? It is still possible because we have an MMU, and if as a system programmer you have taken care of configuring the MMU properly, maybe whenever this guy is generating 80,000, you may refer to maybe if data is starting at 10,000, assume, okay, 10,000 X. Then as long as whenever 80,000 comes, you want memory to MMU to generate 10,000. So it's a relative. Okay, from here to that 10,000, 80,004 may convert it into 10,004. So effectively, what happens is during the runtime, this address keeps on translated. Okay, it is going to be translated for every instruction access. It's not done for once and then forgotten. Every access, wherever there are some load LDM or STM is involved, this transition happens. See, remember, in this instruction the translation is not happening because this is only moving a constant into the register R2. which is stored here as 80,000. Maybe in the code 80,000 is stored as a part of the code that gets copied into R2. But when this instruction is executed, this R2, whatever is the content of R2, is going to be put on the address bus. So that 80,000 is going to come out when this instruction is executed. So at that time, MMU is active, looking at the address, and then it translates it. So it translates not only the addresses generated by the LDM and STM instruction, it also translates the code. Suppose this code is residing in the original program, okay, it is residing at 45,000, assume. So the instruction R15 will be initialized with 45,000, and it will be generating this address to access the instruction. Now that time also MMU comes into play, and then if suppose code is loaded at 5,000, doesn't matter as long as it is matching with the size where this particular page is starting. Then this 45,000 what is generated to access the instruction also gets modified. So every address generated to access the instruction, as well as any instruction that is generating an address for the LDM or STM instruction, gets modified by the MMU in real time, dynamically based on the configuration of the MMU, so that a proper address is generated, which is going to the physical memory which is in the system, and it gets accessed. So effectively, what the programmer thought the code is, where the code is, and where the data is going to be residing is completely different from what the assumption the programmer had. So when I say programmer, means the programmer who is building the executable and then locating the different parts of the program in different parts of the digital memory. It is real time modified to access the different locations in the physical memory. So this is what is happening for every address. So you should have this, you should understand this particular translation. So to the actual physical address, okay, the MMU translates it to the actual physical addresses where the programs are stored in physical memory while they are executed. Okay, this translation process allows programs to run with the same virtual address. So still the processor, when it generates the addresses for accessing the code or accessing the data, it generates the original virtual address the programmer thought. Okay, there is no change because the programmer has built the executable assuming the 80,000 and 40,000 as the code and data. So you cannot go and change the code unless you build it again with a compiler and linker and a whole lot of things I will be talking about in the subsequent lecture. So unless we change the code generated to accommodate the new address, it will continue to assume that this is the address the code is residing and this is the address data is residing. So if the code is assuming this, then what ARM executes will also be doing that. So we have to take care of that in the MMU. Similarly, if the programmer is thought that code is residing in the particular location, the R15 will be accordingly modified to access the original virtual address only. So because all the examples, suppose within the code there is a branch, and then the relative addresses it computes will be based on where it assumes that code to be. If it is an absolute long jump or something, then it will generate the same address. Okay, it will replace the value in R15 with the original virtual address which was thought of the program is supposed to be residing. But because we are in between, we are moving it to some location which is different from this, we have to take care of so we are locating it somewhere. So we have to take care of changing the translation. Okay, in runtime. That is either it is a job of OS, or I assume that as a programmer you may be developing an OS code also. Okay, in that case we should be aware of all these things. Or as an application developer, you should be aware of these things do happen in the system. Okay, very good. So while being held in different locations in physical memory, the execution happens. Now let me again just give you a brief overview as well as the differences between MMU and MPU. The primary difference between MPU and MMU is the addition of hardware to support virtual memory. So if I say this is MMU, okay, it has got virtual memory support. Okay, and then what all you saw, what are the features are supported by MPU is also there in the MMU. Okay, it's all comprehensive in one place. It's done in one place in the one module. So the MMU, however, also expands the number of available regions. So one more additional thing is, if you recall, MPU, I said that there can be only 8 regions. So the limitation came, okay, because it maintained, if you remember, C0 to C7, the secondary registers of the coprocessor 15, okay, of C7. I think the primary register was something, and then it was doing, okay, some primary register, and then the secondary register was only 8 registers were there, and each register was holding some information about the access permission and what is the write buffer, and every there were another register to manage the cache and the write buffer. So all these three units were controlling one region of the memory. So we said that region had a 0 to 7, 8 regions were there, and each of them have a different based on the number. Precedence was more, maybe higher regions will have higher priority number. So that their attributes will take over ownership. Okay, take over as whenever a task is running. Those things we saw. So these were only limited 8 regions. If we have continue to have 8 regions with the support of MMU also, then it is not possible to support many tasks. Okay. I said multiple tasks can be run. In the MMU we are bringing in because we want to run multiple processors. And when I say multiple processors, they will have multiple pages, code, stack, data. Inside that's also the huge, because they are all huge. There will be so many number of pages all there for each of them. So based on the process as well as based on the type of the memory, the regions will be different. So with just 8 regions supported, we will not be able to achieve whatever we want for a multiprocessing system. So what happens is, this multiprocessing system actually is possible with the help of MMU. So MMU manages multiple regions, not only limited to 8, multiple regions, because it is maintaining it in software. That means it is having a page table, and it is the page table itself is maintained in the main memory, so there is no limit on number of registers. So whenever a particular code is to be run, that time maybe one of the registers in the MMU will be configured so that particular region gets active. So it is not restricted as in MPU. Okay, so that you should have in mind. Expands the number of available regions. MPU had a limit on number of regions to be 8, since it was maintaining it in registers. Now MMU maintains the regions attributes in page table, which are held in main memory. So once it is the page table is there in the main memory, the number of entries, page table entries can be many. So it doesn't matter, okay, how many regions you are defining. For every process, there I told you that every process has its own page table. That means P1 will have its own page table, P2 will have its own page table. Okay, so the number of entries, each entry will be corresponding to one region. It could be a page meant for code, or another entry may be a page for the data. It could, multiple code pages will be there. Like that, the many are there. There is no limit. Okay, in the sense there is some physical limit, which I will tell you once you know the number of entries in the page table and how many pages you can have. It is it's not infinite. Okay, no system in a physical world can have infinite possibilities. Okay, but it is not as low as 8 regions that MPU says. Okay, very good. Now, what are the attributes, region attributes that we saw in MPU? We said that okay, we can say data, multiple sizes, start size. We can have different start addresses we can give, and then we said that starting from 11 to 31. Okay, 2 power 11 to 2 power 31. If you recall 5 numbers, n was there, 2 power n plus 1 was there. Okay, so we can have a pages of size 4 kilobyte to 4 GB. Okay, the page sizes, and then we said access permissions can be either read or write or no access, and then cache can be write back or copy back, and then the write buffer can be enabled or disabled. So all these are possible. Now MPU had a limit of 8 regions, whereas in MMU we can have any number of entries. The maximum limit will be the number of maximum page table entries that it can be supported in the system. Okay, that is much more than 8. Very good. Now let us go into virtual memory transmission. Okay, this picture should be familiar to you. Okay, because in the last session we talked about virtual memory and physical memory, and then how a page, okay, gets translated to page frame in the physical memory. So this is the virtual memory, this is the physical memory. So this corresponds to M1. Okay, that's main memory. Now a task. Okay, now I am calling it a task or a process. Both can be used, synonymously. So we assume that a task is starting at this location address, and then it has got all the regions in it. Okay, it has got code, data, stack, initialized data, whatever it is, all of them are there in this area. Now whenever this task is running in the ARM processor, okay, the addresses that are generated for accessing the code as well as the data will be residing in this range only, will be coming in this range only, correct. So that addresses come out, and then it will all be having a base of 400. Now suppose you are maintaining in MMU a register, it's called a relocating register. Let us call it a relocation register because we are relocating this address to some other address, correct. So it is called a relocation register. Is basically a page table entry. Okay, so this relocation register, what is this? Whenever it sees 400, it replaces with some, say assume 800. Okay, now effectively what happens? This is going to this address. Now what is the requirement in the system? In the board that you have, ARM is there, and then physical memory is there. Now there will be some address decoder in the system. Whenever the address is coming, now address is coming to the decoder from the MMU because MMU has translated it. So whatever address coming from ARM processor is coming to MMU, and MMU translates to now 80,000. Now this address decoder will look at this 80,000. Okay, whatever this address, physical address coming out from the MMU, and then suppose the memory chips have a chip select and whatever address enable, all those things. So it will enable the chip with that memory. So in fact it maps to this address. So in the physical memory we can keep the code or data meant for this task 1, so that ARM can run it. Okay, so this is what is happening. Now MMU is having this relocation register. So whenever it sees this 400,000 something coming out, it replaces with the address where the actual memory is there. So how we program the MMU? Before programming the MMU, okay, this is the MMU. Before programming MMU, we should be aware of where the physical memory in the system is and what is the address they are, and which are the addresses not valid. All this should be known to you. Then really, as a programmer, as a or the OS should be configured if it is done by OS, or if you are writing a small microkernel, or you are having the responsibility of initializing the MMU, then you better know what the MMU main memory is, where the main memory is in the system, which address it is actually located, and then where the programs are located, and then accordingly initialize the memory MMU so that we get a conversion. Okay, very important. I hope this is clear to you. Let us see. Another task compiled to run at the same virtual address. Now I am bringing in another task. Okay, see, task 1 may be done by a person A. Okay, task 2 you are given to another company. It could be another company or another person in the same company. He is writing another application. They don't know each other existence. Okay, they don't even know that the program that they write, the application they write, are going to run in the same system. So how do we expect them to know to not to overlap the address space that they assume their code is going to be? We cannot assume, and we don't want the restriction too. So what happens? As a programmer, I have a freedom to assume whatever address I want in this space. Okay, the whole virtual space is available to me as an application developer. I say This is what I am assuming my program is going to be, and then I will inform the OS vendor, or it is all, it's not that we send a mail about this, it's all captured in the executable itself. Okay, when the executable is built, it will have all the information about what the assumptions are. Now OS, when it is loading the executable, okay, into the processor, it will do the job of configuring the MMU. Okay, it's not done manually. Okay, it's all done using the OS. Okay, otherwise if you are writing a kernel, maybe you should do that. So then what happens, these addresses, it doesn't matter whether task 1 is assuming this or task 2 is also assuming the same address, no problem, as long as you know that ARM will only one processor is there, either T1 or T2 will be running. So whenever T1 is running, I may assume the translation is like this. Whenever T2 is running, I will assume another translation, but I will configure the relocation register in the page table entry in the MMU so that proper address is accessed or proper address is generated. So a virtual address can be run by simply changing the value in the relocation register by mapping the task to a different location in the physical memory. Now suppose though T1 and T2 are not running together, but they may be residing in the memory. Okay, I suppose I want to keep task 2, okay, in this location. Assume that this memory is also there. Maybe it is at 70,000. Okay, I don't know. It's not 70,000. 700, 7,000. Okay, 6 zeros are there. In this address, it is there. Now what happens? Whenever T2 is, but T2 is also originally built assuming that this is the address, but doesn't matter. Whenever T2 is running, this location register will be converted to this value. Okay, so what happens now? This task 2, whenever it is generating a address, it will go here. Okay, it will be converted into 7,000, 70, whatever, 700,000. Then it will start accessing from this location. So effectively, what happens is both this and this memory code or data can reside in the physical memory, and then based on who is running in the particular time, that will be translated according to the entries here. So you have to modify this entry here so that it goes and looks at the other area. So this is done by OS when it is loading the process. That's what we are saying, swapping in, swap out, or context switch. Okay, very good. So whatever pages in the virtual memory is called page, and what is converted into a page in the physical memory is called page frame. That's the convention, that is used by all the OS fraternity. So we should be aware of that. Now multiple relocation register. Why do we need? As I explained you, multiple processors may assume different. We need to have a different mapping from virtual to physical. So an area of virtual memory is known as a page, and area of physical memory pointed to by the translation process in a page frame, and the ARM MMU hardware has multiple relocation registers supporting the translation of virtual memory to physical memory. Okay. So it will have multiple relocations. It is not restricted to one register. So I told you that we will modify the entry there. It doesn't, we don't have to have a limitation of number of registers there. We can have multiple registers, and then if task 2 is running, it will access another register, and which will point to the 700,000 address, whatever. So MMU system must be able to translate many pages to many page frames. Okay, that is a requirement of MMU. Otherwise, if it also has some limitation of 8 pages only or 100 pages only, then it will be very limited support. Enabling many processors tasks to run in a system, though it is limited by its physical memory. So basically, what happens? We are able to enable many processors to run in the system, though there is a limitation of memory. Okay, good. Now I briefly explained about this. I think you should have a very good clarity on this. But let me just tell you, once you know physical and page frame and pages. So what is the translation look ahead button? Nothing but the cache, but it is different from the data cache and insertion cache that we talk about. Okay, it's a totally a different hardware entity. It comes into play only when there is an MMU. So MMU, it does a translation. It does a translation from virtual to physical, and for that translation, any 32-bit address coming will be translated to another 32-bit address. That means any page number here will be replaced with a frame number here. Now you can imagine if there are so many processes and so many pages, then this to this conversion there will be so many entries. Now to perform this, we don't want to go to the page table because page table itself is in the memory. Okay, page table only is having this translation information. We saw the relocation register. Page table is nothing but a relocation register, set of relocation registers. So every time we need to access the relocation register, okay, and then find out what is the frame number and go to that particular page to access the page. But that will be expensive because we have to have, I explained that two memory accesses will be involved. To avoid that access, extra access, okay, first time when you have to do it anyway, okay, you cannot escape from that. But once the first access is done, we know, okay, okay, if I have for this particular task, if I have a mapping like this particular page number comes, this is a page table. So this combination, this mapping is actually a 4-byte entry. Okay, each page table has a 4-byte entry. That's all, nothing much. Though page table too many entries are there, but each entry is just a 4-byte. That is also 4-byte. Okay. So everything what you see in ARM world or any specific processor is will be a 4-byte entity. So the page table entry is 32 bits. Okay. Okay. So what we do, we keep it in a cache, which is a high speed cache. Whenever any address generated, it will come and check whether the translation was originally what was there in the page table is cached here or not. If the page was not at all accessed, then maybe this page entry will not be there. If it is not there in the look ahead buffer, then it goes and accesses from the page actual page table and then makes an entry here. So its default it becomes an entry here. Okay. So then next time when it is generating addresses which are subsequent addresses, it will go access from here. So the translation happens within the same page. That's the advantage. Again page, it goes to page table, then page, it gets the page table, page frame. This is the order. Okay. And then once it has accessed the page table, then next time onwards 1, 2 and 3. Okay. So this going from 1 to 2 and 3 are in a single cycle. It's not one memory cycle. Memory cycle is not single cycle. Okay. It will be multiple cycles. But when I say single cycle means M clock. Please remember. Okay. Master clock what is there to do it ARM is running. Good. So TLB caches translation caches. It caches the translations of recently accessed pages. So it is a cache. It is not caching the we call the verb. Okay, caching the data or instruction. It is not caching the data or instruction. Okay, it is actually caching the translation of addresses. So it could be for both instruction access as well as for data access. So anything whether we want to access the data or whether we are accessing the instruction, the ARM processor will be generating the virtual address. So that address, when it is generated, it will have a set of addresses will have a fixed translation. Why I am saying a set of addresses will have same translation? Because suppose you assume 4 kilobyte of page. So if the 4 kilobytes, suppose this is the 4 kilobyte, okay, this will be sitting in this place, right? So within the 4 KB offset, there is no change in the mapping. Okay, this starting address is changing to this starting address. Afterwards, +4 if you do the same +4 only you will be doing here. So the offset portion only changes. The base address doesn't change. So within 4 kilobyte of the page, the translation is not changing. And you know that because of the locality of reference or nearness, all the addresses what you whether instruction or data will be most of the addresses will be within the page. So every time when another instruction is accessed or another data is accessed, we don't have to newly go and find out what is the translation. So once we know that address within the page, if any accesses come, it will be there anyway. The translation is same, so we can use this. Okay, that is why the TLB caches the translation of recently accessed pages. Please remember, it is recently accessed pages because number of entries in the translation requested buffer is limited. It could be 16 or 32 or whatever. The latest processor may be having more, but it is still is not too many. So recently accessed pages will be there. So the replacement policy of this cache is always LRU, least recently used. That means we will be replacing the entry which address the translation which was not used for quite some time, that will be thrown out. Okay, and then we will keep this translation because before the latest entries so that the translation happens for all the recently accessed pages. So it is really a fully associative cache of 64 rupees. Okay, whatever no, the number of entries are 64. Okay, this is what we will be looking at. Okay, but there are some other implementations where there may be more entries. Okay, so we have to manage it with the 64. Now, why is it fully associative? Because the whatever the page address, page number, okay, whatever is coming, the upper portion of the address, you do the content addressable memory scan so that we can find out whether that entry exists or not. If it is so, then look at that value, get the page frame number and replace it with that and get it here to access it here. So it is a fully associative cache. What does it contain? It has a page table entry. Each of them has a page table entry, and please remember page table entry is of 4 bytes. Okay, nothing more, 4 bytes. So there are 4 bytes of 64 entries in the translation Lucasite buffer. Good. Now let us go to page table. This is a very crucial part of the discussion. Please pay attention closely because if you miss, it's very difficult to follow. A page table entry in a page table contains the following information about the virtual page. What are the information? Physical base address to be used to translate the virtual page to the physical page frame. Okay. So the base address to be used to translate the virtual page. So virtual page, what is the base address at which, and that has to be translated to something else in the physical media to the page frame. Access permission. So as I told you, the page frames, the access permissions are now same for a particular page. Okay. So if you remember, I said that it is maintained in the page table entry. Access permissions are maintained in the page table entry. That means we can have access permission like whether write buffer has to be used or buffer has to be used, cache has to be write back or write through. That decision can be taken at a page level. Okay, and so they are assigned to the page. Whenever the address a particular page table entry is used, the access permissions belonging to that page table entry will be looked at. So cache and write buffer configurations for the page. So that is also used here. This means that access permissions and the cache and the write buffer behavior are controlled by a granularity at a granularity of a page size. So it is at the granularity of a page size. Okay. Now it provides finer control over the use of memory. So once if I say that a page size of 1 kilobyte or 4 kilobyte can be there, then we are having a finer control on how a particular page is accessed, how it has to be, what are the access permissions have to be given. They are all controlled at the page level. So regions in MMU are created in software by grouping blocks of virtual pages in memory. So a region can be a group of pages. Okay, so we can have a different access permissions also at the page table, page table entry. So now you see a region is like this, and we have a region 1, 2, and 3, and individual regions have a different pages. So the access permission could be different, but they can be all fall under one region. So and the stack can be at different locations, and each will have a different page table entry. So the sizes of page tables also can be configured based on the MMU configuration that I will be talking about. So you see this here. A flash is used here for pointing the region which is code. Actually, text is another name used in the literature to mean code, to refer to the code. So code can be in flash. The data cannot be in flash. Okay, it can be sometimes. Okay, it can write into the flash also, but it is very time consuming as well as number of these erasers on the flash will also be limited, and it is time consuming and it involves a lot of time. So while running the program, you cannot use a flash for storing the data. Okay, maybe you can, the flashing itself is a big sequence. Okay, lots of time it takes to flash contents into the into the flash. If you want to write into the content flash, it takes a lot of time. So, but reading is fine. Okay, so code can be kept here. So that's why this whole thing is pointing to this location. So code is running from here. Typically, some places, even in systems, we might copy the code into the data, RAM area, and then the code is accessed from here for a faster access. Okay. In this case, it is shown as if it is the code is mapped to this flash. So flash is a physical memory, please remember. So it is a part of the main memory, maybe in this situation, and this part is a RAM. So code and data are mapped to this location. This is a physical RAM available. It could be a DRAM in the system. So this is how the translation happens. Now multitasking with MMU. Let me explain this. Already we talked about this when we discussed MPU. So each task, let us look at the task, and each task assumes the same address as the visible memory starting address. Okay, it could even assume the same size also. It doesn't matter, but they all assume that their task is running sitting in this location. But if you see in the actual memory, they are placed in a different location in the physical memory. And at this moment, task 1 is running. Okay, the translation now takes this address to this entry, and then it generates a physical memory address, and then it gets accessed. But when this task is running in the processor, OS takes care of making sure that this entry is used to translate to this. Apart from this, you can see that the gray portion of the other area which gets protected by the background regions, which we talked about in MPU. So I don't want to repeat those things. So this, because this is this is used as a region. This the PTE entries, the page table entries of this task is access permissions and all the region values are taken. So these will not be accessed. This area will not be accessed when this process is running. Similarly, when task 3 is going on, it will access only its own area. It will be blocked from accessing the other task area. So this is active and this is dormant. White is active and gray one is dormant. So this is explained earlier. So I am just refreshing the memory, like we are refreshing the memories here. So activate different page tables to execute different tasks on a context switch with overlapping visibility, because all these tasks are overlapping with each other in their own space. But when a particular task is running, only this is visible. This is not even there because the task is not done. So nobody is assuming that there is another task. So task 2 sees only its existence. It doesn't see the existence of others. Okay. Only OS knows what are there in that system. Okay, multitasking and MMU. So page tables can reside in MM, and not be mapped to MMU hardware. Okay, why is this condition? Page table can reside in main memory, but not be mapped to MMU hardware. Can you think of a reason? Let me explain. So processor is here. Always my processor is at least to the size now for the ARM. Hope ARM will object to this. MMU is here, and then we have a main memory. What I am saying here is the page tables can reside in main memory. Okay, good. I want the page table to be somewhere here. Okay. Page table, you know that it is having the information about how to translate the entry. So page table entries are here, multiple page table entries. It is also residing in main memory because you can't be in a register because the number of entries are huge. So it has to be in the main memory. Now, why do you need a page table? Okay, if I write it here, you will know because I am writing it and typing that, then you will not know what I wrote. So PT is here. Okay, entries. Now, what do they have? They have the translation information, relocation register information. But if I say that even to access the page table, I need the help of MMU, it is like expecting something which is not possible. See, we want to look at these values to configure the MMU, correct? Because now MMU is raw, it is not even configured. Assume that it is like a chip sitting there without any information about what to do when a particular address comes. What do I generate? It doesn't know. It is still uninitialized. Now to initialize it, I need the entry, page table entry. Okay, because the processor doesn't know itself, how to configure the MMU. It has to read the instructions, OS, code, and then OS will be already would have generated the PTEs, and then it will know that the page tables are residing in the memory. So it will say that you read these entries from here, and then accordingly you configure it. So to do that, if this we need the MMU entries, then it is impossible to configure the MMU. So that is why page tables are always mapped, okay, from virtual, that is also virtual space, to main memory one-to-one comparison. That means a virtual memory address 1000, okay, will translate to 1000 only in the main memory. There is no translation of these addresses. So in that case, if there is no translation, then we don't need a MMU for that. So then we are free to access the page table. Oh, very good. Now I am able to access the page table without the help of MMU. Now using the page table, I can configure the MMU entries. In that case, then if I generate some address, it will translate it properly. So it is like we need this information to configure it. So we cannot use the MMU for doing it. That's why the page tables are always one-on-one mapped to the MMU hardware. Okay, it is like let's say it is not mapped to MMU hardware, and the addresses are one-to-one. So there is no difference between the virtual address and physical address of page table. That's what I'm saying. It is same. So then we can short circuit MMU, right? We don't need MMU. The addresses will be, as soon as these addresses are generated, it will not even enable MMU. It will go into the address bus directly without any translation. Okay, that is also a job of the decoders in the system. So multitasking system is created using separate set of page tables, each mapping the virtual memory space and each task to physical memory. This I explained already. To activate a task, a set of page tables of a specific task is mapped into to be used by the MMU. So whenever T1 is running, that table will be there. When T2 is running, task 2 is running, another page table will be there, and MMU will be configured accordingly. Who does it? OS does it. So OS is residing in an area where MMU need not be there because it is residing in an area which is one-to-one from virtual to physical. Okay, including the page table entries, everything is one-to-one. That is why I am calling the OS as a lower area where we don't need to access them using MMU. So other sets of inactive page tables belong to other dormant tasks that you know. Now what are the steps in context switch? Again I will tell you, save the active task context and save the task in a dormant state. Okay, flush the caches. Flush the caches is very important. That means that possibly clean the data cache if using a write back policy. See, as I mentioned in the last class, clean is different from flush of a cache. Okay, clean means the cache entries are made invalid. Okay, if suppose the data cache is there and then they were all dirty bits are there. Okay, that means these entries are modified. So we need to write this cache entry into MM. So clean means we have to make these entries invalid. Before that, we have to make sure that it is returning into the main memory. Okay, we are writing it. But if it is a flush, we don't care about writing back. Okay, for a code instruction cache, we don't have to write back this instructions which are there in the cache. So we can just say flush the entries. Similarly, the TLB entries, okay, the translation lookers at buffer entries are basically a page table entries, right? The page table entries are already there in the memory. Only thing is for speed access, we have copied it into the TLB and then we were using it. So this page table entries are not modified. There is no dirty bit associated with the TLB entry because it should not be modified. The translation is decided by the OS and we should just go by what was the translation to be done. So page table entries are not modified while they are in the cache of the TLB. So we don't have to write back this entry into the main memory. We can just flush it. So that's why we call TLB has to be flushed, and then data cache has to be cleaned, and instruction cache needs to be flushed. Normally we don't write back the instruction. So I hope this is clear to you. Let me change the color. We have used this color so long. So flush the TLB entry. Okay, we will not clean the TLB entry, we will flush it. Whereas data cache has to be cleaned. You hope clean means we are writing back into the main memory. Here we don't write back, we just make the entries as invalid. The entries in the cache. So configure the MMU to use new page tables, translating the virtual memory execution area and data to be awakening processes. So what we say is we are configuring the MMU for the new location which is coming. Awakening task, whichever new task is coming into, after context switch, what happens? The new task is coming. So MMU should be using the new task page table entry. So we will be using that for that. Restore the context of awakening task. Restoring the context means we are restoring it, the registered values which were there, the values of R13 and R14, R15, all those things have to be restored. Where is it restored from? It is restored from the OS. OS is maintaining some TCB, it's called task control block. It maintains the information about when the task went out, what was the values of the registers. It maintains in the task control block and then writes back into this location and then cleans the caches and then starts this new process to run. New process comes into our processor and then starts running. So this is the job done. I am reiterating these sequences so that as you gain more knowledge on MMU and cache, you will be able to appreciate these points much better. So it will be very good to know what's happening when a context is happening. Resume the execution of restored task. That means what? Whatever value was the R15 of the new task, that will be now generating the address, and the MMU will be translating it very sincerely. Okay. Good. Now we have come to the main topic of discussion, MMU organization. Don't get perturbed with this. Okay, I'll explain. In the processor, ARM processor, okay, we have two page tables. Okay, only two levels of page tables. I'll explain you what is the need for it. Okay, the first one is called L1 and second one is L2. The L1 is the master page table. The master page table, what does it do? Let me tell you. See, you know that overall there is a 4 GB of space, nothing more than that. Virtual or physical, it cannot be more than 4 GB because 2 power 32 is the maximum address we can generate. So we can't access beyond this. Whatever gimmicks we do. So this 4 GB address, if I tell you, it is split into 1 MB each. Okay. 1 MB. Then how many we will have? There is 1024. Okay. Into 1 MB, 10 power 6. That many entries will be there. That is, this will be from 0 to 1023. Why 10 power 6 into 10 power 3 is 10 power 9. So GB is what? 10 power 9. Okay. Now actually, okay, 4022. Sorry. Okay. This will be 4. Why? Because this is 1 MB only, right? This can go up to 4 GB. So 4024 into 10 power 6 is what you will get as a 4 GB. If you simplify this as a 4K, 4 into 10 power 3 into 1 MB is I am simplifying it as 10 power 6, which will become 4 into 10 power 9. That means 4 GB. So if I decide to split the 4 GB of memory, which memory? The virtual memory, into 1 MB of 1 MB sections. Okay, if I call it as a section, okay, then I will have how many entries? 40. I think it's not 2496. Okay, 4096 absolute term. But for simplicity, say let us assume it as a 4K. So that many entries will be there. Okay, correct? Sorry, it is 9. Okay, 4096. So that many entries will be there. Now the master page table is having how many entries? It will have 4K entries, right? 4K entries for 1 MB of page. So how much of size we need for the page table? I told a page table, okay, will have 4 bytes of content, okay, 4 bytes only. In that case, if I say that to say, since I split this 4 GB space into 1 MB and I am keeping one entry for every 1 MB in the page table, then there will be 4096 4K entries into 4 bytes each. So totally it may occupy 16 kilobytes of space. It is fixed 16 kilobyte we need to keep this master page table in the memory. There is nothing like less than this. Okay, it has to be provided. This much of space has to be reserved. We cannot have the system without with the MMU support, and then you have to keep this entries because we have to know the fault entries also. I will talk about the fault entry. Assume that this is the kind of a space allocated, and then we are having a memory, a table, a master table in the memory, okay, which is one map directly. So we are not using to access this. We are not using the MMU, but after accessing this entry, we will be using the MMU. Okay, because based on the entries that we have. So if that is the entry, it will be pointing to the system entries, will be pointing to the another table. Okay, one more table is there. Let us not worry about it now for a moment. So this is done to actually within 1 MB. I want to give a different access permissions. Okay, in that case, then I have to split that 1 MB also into finer pages. So if I need that, if I want to different access permission, then I need different page table entries, no, because we have to have different access permissions for each page. In that case, we need to have one entry for each. In that case, we will be having another entry which will be pointing within that 1 MB location, and then referring the first maybe to 1 kilobyte or 4 kilobyte, whatever it is. That part of that 1 MB will be based on this entry, and then the next will be based on this entry, like that. There you will be having an entry for 1 MB location. So let me summarize. There is physically or in a virtual space 4 GB of space only is possible. That virtual memory is split into 1 MB each. In that case, there will be a 4096 entries, 4096 sections will be there of 1 MB each. So we need one table which is called a master table, which will translate where this particular 1 MB space in the virtual space is in main memory. So we need to have 1 MB for each of them. But please remember, not all these are there physically. We may assume that 4096 pages are there, 1 MB sections are there in the virtual memory, but actually physical memory may support only 10 of these sections. But doesn't matter. Okay, as I told you, we can always bring in some value and then throw that into secondary memory. So we can always manage this many entries. So, but this entry as such should be there, which is occupying 16 kilobyte of space, because each entry of needs a 4 byte of value. So 4K entries into 4 bytes is 16 kilobyte of entry. So this page table needs to be physically present in the memory, which is not mapped to the MMU. So it is one-to-one map. This wherever this page table is residing can be accessed without using the MMU. I hope all my words are well received, understood it. But let me rephrase it once I show you one more example. Okay, let us see that. Now page tables in MMU. Now let me summarize this now. I said level 1. Let us talk only about level 1 now. Okay, don't bother about level 2 for a moment. Okay. Okay, let me. Okay, so I need to